We've talked about what k-fold cross-validation is, but we haven't really talked about how to choose k. What is a good value of k to choose? So let's talk about how to choose k for k-fold cross-validation. And so let's think about, so what are we doing? What should be our criteria for choosing k? Well, let's go back up here to the beginning. We were thinking about what is the purpose of cross-validation? Well, the purpose is we want to choose, of course, we want to choose a good model from this set of this finite model class of models. And our criteria for choosing a good model was that we wanted it to have low expected loss. We don't have this low error, epsilon m, and m with a low epsilon m. And so what we did, right? We wanted to have a low epsilon m, and what we did was we constructed this estimator, epsilon hat m. We estimated epsilon m with the procedure, the k-fold cross-validation procedure. And this is actually, if we think about the data as being random, we think about the data as being random IID samples from this true unknown distribution P, then this estimator, this epsilon hat m, is a random variable that depends on the data, since the data is random. And it also depends on, of course, our model. Like, so epsilon m hat would depend on m, of course, the model, and it would depend on the data, and it would depend on k. So it would be, so let's write down here. So what is this thing? So we wanted to estimate this. So we constructed an estimator epsilon hat m, and let's denote the k. Let's put a superscript k. So before I was using this to denote the sort of error for each round, before. But this is different. Now this is k, so the k denotes the k in the k-fold cross-validation. So it's an estimator of epsilon m. And we've talked before about how do you choose a good estimator? And if we thought, if we wanted to use some, what does it mean to have a good estimator? Well, we need to have some loss function, right? If we're thinking from a decision theoretic perspective, and we are, then we need to choose a loss function if we're going to evaluate these, if we're going to do it in a principled way. And let's choose. Well, let's see. So these are continuous valued things. These are real valued things. So let's choose. Well, let's just say epsilon hat m. Let's choose the square loss. That's a natural sort of loss function in this type of problem. And so we want to choose an estimator that has small expected square loss. And that is, of course, the mean squared error, right? That's just the definition of the mean squared error. And I could also put here, this also depends on the data. I could put data depends on the data as a random variable, depends on the data. Well, let's drop that but just remember that it's a random variable that's a function of the data. And the randomness comes from the data, since the data is random. So the mean squared error we talked about, remember we talked about the bias variance decomposition. Remember, the mean squared error can be decomposed as the bias squared plus the variance. That's the bias variance decomposition. And so in order to choose a good value of k for this estimator, we need to find a good trade-off between bias and variance. So in some sense, this is sort of a very interesting sort of introspective thing, right? Because we need to choose a good value of k, and in some sense each different k is sort of, it's this parameter, but the whole point of doing this procedure in the first place, the whole point of doing cross-validation, was to choose a parameter m for, it was sort of the model selection parameter. So in the process of choosing a model selection parameter, we need to choose a parameter for our process for choosing the parameter. So let's think about how we're going to choose this. Let's think about in terms of the bias and the variance. What makes sense? Well, when k, let's use a color now. Let's think about what happens when k is large. Like, for example, i.e., when k is n, when k is the total number of data points. When k was n, that was leave one out cross validation. And in leave one out cross validation, so let's go back up to our data here. In leave one out cross validation, we took a single point, each example in our data set was a fold. So this was the first fold. So we trained on all of this, and then we evaluated on this on the first round. And then we took the second point, we trained on everything else, and then we evaluated on that for the second round. So when k equals n, that's what we're doing. And let's think about it. Is the bias low or is the bias high? So let's go down here. Let's look at this. Let's look at this picture here. Is the bias low or is the bias high? Well, when k equals n, the training set is almost the entire data set. So each of the sort of on the first round or on any of the rounds, the function that we get, the prediction function that we get, the classifier or the regression function that we get, is going to look very, very similar to the final thing that we get, the one that we would get if we trained on the whole data set, because we're only leaving out one point. So each of these is going to be fairly representative of the whole, the resulting thing. And since we're leaving out one point, that's independent of all the rest, then that's going to be a fairly good indicator, fairly low bias in terms of its indication of the error for the final thing. So the bias for this is going to be low bias. On the other hand, what's happening with the variance? So let's think about the variance. Since each of these guys, if we had some sequence, fm1, fm2, each of these prediction functions that we constructed, they're all going to be very similar, right? But they all depend very, very highly on the data. And as a result, the resulting, this estimate is going to be very, very sensitive. The estimate that we get, this epsilon hat m, the estimate that we get of the error is going to be very sensitive to the particular data set that we get, right? It's not going to be, these are not going to vary a whole lot. I mean, they'll vary depending on the error will depend on, each of the points, but the classifiers themselves are going to be fairly similar. And since they're so highly dependent on that particular sample of data that we got, it's going to be fairly high variance. If you wanted to have low variance, you would want to estimate over a very sort of wide range. You'll get a whole bunch of samples of data 1, data 2, all independent. And if you were to average over all of those, then you would get low variance. But this is highly dependent on the very one particular data set that we got. So this has high variance. It's good, fairly high variance. So now what happens when k is relatively small? Let's say, e.g., I guess I should put this is e.g., not i.e., for example. For example, so when k is small, let's say around 5 or so, or 3, 4, 5, something like that. Then what's happening with the bias? Well, maybe we would think it's going to be high. Let's think about that. So when k is small, well, it's this sort of more Well, like this picture. Well, when k was 5, this is the picture. Actually, let's make it even smaller in order to be just to really sort of see it clearly. Let's say k equals 2, super small. Then what's going to happen? What's going to happen with the bias? Well, in that case, our training set is only going to be half on each round. Our training set's only going to be half of the data, d. And as a result, the resulting, each of these functions are going to be probably do much worse than if we trained on the whole data, because we're only getting half the data to work with. So as a result, we would expect these to really not do as well as if we had trained on the whole data set. So this is going to be biased towards lower, or rather, this is going to be biased towards higher error. Our estimate of the error is going to be higher because each of these guys is not going to be as good. He just doesn't have as much to work with. So this is going to have higher bias, and it's also going to have lower variance. So that's for k small. And so in order to find a good trade-off, so people have done lots of experiments and also theory about k-fold cross-validation. And so the common wisdom is that a good sort of balance between these two is, so we'll put it here, so we'll say a recommended value of k is k equals 10. This is sort of maybe the standard sort of choice of k to use. Sometimes people use 5, but k, 5 or 10. 10's sort of the recommended number. All right, so that was kind of interesting, right? That was kind of cool because we were thinking about, it turned out that in order to choose k, this was sort of a complexity. This was sort of a complexity parameter, right? Choosing k was a complexity parameter, and we were using it to choose the procedure that we were going to use to choose the complexity parameter. So there's something sort of very interesting and introspective in there. And if you wanted to get really crazy, I mean, this would be totally silly, but you could even imagine doing, k-fold cross-validation to choose k, right? But I don't think anybody actually does that. But you could, and that would be sort of interesting. So that's k-fold cross-validation, and I hope that was all very clear and interesting to you. And I think k-fold cross-validation is probably one of the most widely used types of model selection. So it's definitely a very, very good thing to know how to use and understand how it works. And before wrapping up, I want to say one more thing to compare k-fold cross-validation with Bayesian methods. So we talked about Bayesian methods for model selection, and we talked about k-fold cross-validation. And just one sort of thing to point out is that with k-fold cross-validation, we had this restriction that we had to work with finitely many different models in our model class. And that can be one advantage of the Bayesian methods, is that sometimes Bayesian methods can handle high dimensional sort of continuous valued parameters in a very natural way. So that can be one advantage of Bayesian methods over cross-validation. And so another point of comparison, both methods give you estimates of your error. I mean, that's what the point of cross-validation is, to estimate the error. And you also get the same thing in a Bayesian method. But I think this continuous parameters in high dimensions is one area where you might really want to choose a Bayesian method over cross-validation. Okay, see you later.